1201, Claude responded. Right now, the nearest star to our sun is so far away that if you drove there at highway speeds 60 miles per hour, windows down, engine running without power, right now the nearest star to our sun is so far away that if you drove there at highway speeds 60 miles per hour, windows down, engine running without pause, the journey would take approximately 50 million years. 50 million years ago, the dinosaurs had already been extinct for 15 million years. The continents looked nothing like they do today. The Himalayas had not yet risen. The Mediterranean Sea did not exist. Mammals were small, frightened, tentative things scurrying through undergrowth that would eventually become Europe, and you would not even be halfway there. This is the distance to Alpha Centauri, 4.2 light-years, the closest stellar neighbor we possess. The nearest campfire, in a darkness that extends in every direction for distances so vast that the number 4.2 light-years already sounds deceptively manageable. It is not manageable. It is a gulf so absolute that every ship humanity has ever built, every rocket ever launched, every probe ever flung outward from this world would require tens of thousands of years to cross it. Voyager 1, the fastest human-made object ever to leave the solar system, traveling at approximately 38,000 miles per hour, would need over 70,000 years to reach Alpha Centauri. If it were aimed that direction, it is not. But here is what most people get wrong when they confront this distance. They believe the problem is technological. They hear 50 million years by car and think we simply need a faster car. They hear 70,000 years for our best probe and conclude we need better engines, more efficient propulsion, some future innovation that will compress those numbers into something a human lifetime can contain. They assume, as our species has so often assumed when confronted with seemingly impossible obstacles, that ingenuity will eventually prevail, that given enough time and resources and brilliant minds applied to the problem, we will find a way. Physics has something uncomfortable to say about that assumption. The barrier separating us from the stars is not a technological barrier. It is not an engineering challenge awaiting a sufficiently clever solution. It is woven into the fabric of reality itself, embedded in the relationship between space and time at a level so fundamental that no amount of engineering can address it, because engineering operates within physical law, and this barrier is physical law. The cosmic speed limit 300,000 kilometers per second. The speed of light does not function the way any other limit in human experience functions. It is not a wall you might eventually punch through with sufficient force. It is closer to a feature of the geometry of existence, like the fact that the interior angles of a triangle sum to 180 degrees. You cannot engineer your way to a triangle whose angles sum to something else. You cannot build your way past the speed of light. And yet, in 1994, a physicist named Miguel Alcubierre published a paper that sent a quiet tremor through the theoretical physics community. What he found was not a way to break the speed limit. It was something stranger, something that the equations of general relativity, Einstein's own equations, appeared to permit, a way to make the speed limit irrelevant. A configuration of space-time geometry that would carry a spacecraft across interstellar distances at arbitrary velocity without anything aboard ever exceeding 300,000 kilometers per second, without violating a single law of physics. The mathematics worked. It was elegant. It was rigorous. It was an exact solution to Einstein's field equations, the same equations that correctly predicted gravitational waves, black holes, the bending of light around the sun, the expansion of the universe. These equations do not speculate. They describe, and they describe something extraordinary, a bubble of flat space-time that could propagate through the cosmos, like a wave carrying whatever sat inside it to destinations impossibly distant, in times impossibly short. The catch, and there is always a catch when the universe appears to offer a shortcut, revealed itself only when physicists asked the question that every beautiful theory must eventually face. Not whether the mathematics permits it, but whether the universe does. What they found across 3 decades of increasingly sophisticated theoretical investigation was not a single answer, but a pattern. The pattern of a cosmos that guards its speed limit, not with one wall but with many. A layered defense system, where solving one problem opens onto deeper problems, where each apparent loophole seals itself as you approach where the mathematics grants permission and the physics withdraws it in the same breath. If you have ever wondered why the universe enforces its speed limit with such apparent ferocity, why the cosmos seems almost determined to keep the stars beyond our reach, regardless of how clever our theories become, this is the story you have been waiting for. If journeys into the deep architecture of reality are what bring you here, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach people who are looking for exactly this kind of exploration. Now make yourself comfortable. We are going a long way tonight. Let's begin. You cannot travel faster than light. Read that sentence again slowly and notice how quickly your mind reaches for qualifications. Faster than light with current technology. Faster than light using conventional propulsion. Faster than light as far as we presently understand. The qualifications feel natural because every other limit humanity has ever encountered turned out to be a limit of knowledge or technology rather than a limit of reality. People once believed heavier-than-air flight was impossible. They believed the sound barrier was a physical wall. They believed the 4-minute mile represented a biological ceiling. Each of these limits fell because they were contingent dependent on specific conditions, specific technologies, specific states of knowledge that could change. The speed of light is different, not in degree but in kind. To understand why, you need to go back to 1905 to a patent office in Bern, Switzerland, where a 26-year-old clerk named Albert Einstein was spending his days reviewing applications for electromagnetic devices and his evenings dismantling 2 centuries of physics. Einstein had been troubled for years by a contradiction that sat at the heart of classical physics, a contradiction so fundamental that most physicists of his era simply looked away from it. James Clerk Maxwell, working in the 1860s, had derived a complete mathematical theory of electricity and magnetism. His equations were a triumph of 19th century science, unifying 2 apparently separate phenomena into a single elegant framework. But buried in those equations was something strange, something that did not fit. Maxwell's equations predicted that electromagnetic waves, light travel at a specific velocity, approximately 299,792 kilometers per second. They assigned this velocity as a constant with no reference to the motion of the source emitting the light or the observer measuring it. This was bizarre. It violated every intuition about how motion worked. Newton's physics was clear on this point. Velocities add. If you stand on a flat car moving at 50 kilometers per hour and throw a ball forward at 30 kilometers per hour, someone watching from the station sees the ball moving at 80 kilometers per hour. The ball's velocity relative to the ground is the sum of the flat car's velocity and the ball's velocity relative to the flat car. This is not just common sense, it is mathematically precise, experimentally confirmed, and intuitively obvious to anyone who has ever thrown anything from a moving vehicle. But Maxwell's equations suggested light did not obey this rule. No matter how fast you move toward a beam of light, the light would still approach you at precisely the same velocity. Run toward it at half the speed of light, and it approaches at 100% light speed. Run away from it at 99% light speed, and it still catches up at full speed. The number never changes. The source's motion doesn't matter. Your own motion doesn't matter. The velocity of light appeared to be a universal constant independent of all reference frames. Experiments confirmed this inexplicable result. In 1887, Albert Michelson and Edward Morley constructed an extraordinarily precise interferometer designed to measure how Earth's motion through space affected the speed of light in different directions. If light traveled through some medium, physicists of the era imagined an invisible substance called the luminiferous ether, then Earth's movement through that medium should produce measurable differences in light speed depending on whether you measured along or against Earth's direction of travel. They measured no difference. None. The speed of light was the same in every direction regardless of Earth's motion. The experiment intended to confirm the ether instead eliminated it. And with the ether gone, the constancy of light speed had no obvious explanation. Einstein's response was to stop searching for an explanation within existing physics and instead to accept the experimental result as a foundational truth about reality. If the speed of light is constant for all observers regardless of their motion, he reasoned, then the concepts we use to describe motion space, time, simultaneity must be far stranger than Newton imagined. What he derived from this starting point was special relativity, and it contained a revelation so disorienting that it has never entirely lost its capacity to disturb even people who have spent decades working with it. Time is not universal. This is not a philosophical statement about perception. It is a physical statement about measurement. Two observers moving relative to each other experience time passing at different rates. An observer moving at high velocity relative to you ages more slowly than you do, not because of any biological effect of motion, not because of vibrations disrupting clocks, or any mechanical artifact of travel. Time itself, the actual duration of physical processes, runs at different rates for observers in relative motion. Consider what this means in concrete terms. Imagine a friend boards a spacecraft and accelerates to 90% of the speed of light. She travels for what her clock measures as 10 years before returning to Earth. You've been waiting, watching your own clock. Your clock does not read 10 years. It reads approximately 23 years. She has aged a decade. You have aged more than 2 decades. Neither of you is wrong. Neither clock is broken. Time genuinely passed at different rates for the two of you because you were in relative motion. This is not speculation. It has been measured. Extremely precise atomic clocks placed aboard aircraft and compared to identical clocks remaining on the ground show exactly the time differences special relativity predicts. Muons, subatomic particles produced by cosmic rays striking the upper atmosphere, should decay long before reaching Earth's surface, given their measured lifetimes. But because they travel at near light speed, their internal time runs slowly relative to our ground-based measurements, and they survive long enough to reach detectors at sea level. The universe actually works this way. Special relativity also revealed something devastating about acceleration. As an object accelerates toward the speed of light, the energy required for each additional increment of velocity grows, not linearly, not proportionally, exponentially climbing toward infinity as velocity approaches light speed. To accelerate a spacecraft to 90% of light speed requires enormous energy, but it is at least a finite amount. To reach 99% requires dramatically more. To reach 99.9% requires more still. Each additional decimal place demands energy vastly exceeding the energy required for the previous one. To reach exactly light speed would require infinite energy. Not a very large amount of energy, not more energy than our current technology can provide. Infinite energy, a quantity that does not exist, that cannot exist, that has no physical meaning as a finite resource. This is where the intuition about technological limits becomes dangerous. People hear infinite energy required and think we just need a better power source, a fusion reactor, an antimatter drive, something sufficiently exotic and energetic. But infinity is not a very large number awaiting a sufficiently powerful engine. Infinity means no matter how much energy you have, it is not enough. If you possessed all the energy in the observable universe, every photon, every particle, every quantum of electromagnetic radiation emitted by every star over the 14 billion year history of cosmic time, it would not be sufficient to accelerate a single electron to the speed of light. Not because we lack the engineering, because the mathematics forbids it without exception. But the energy barrier, staggering as it is not even the deepest reason why faster-than-light travel appears impossible. There is something more fundamental beneath it, something that strikes at the logical structure of causality itself. Special relativity demonstrated that the concept of simultaneity, two events happening at the same time, is not an absolute feature of reality, but a perspective that depends on the observer's motion. Two events that appear simultaneous to an observer at rest appear to occur at different times to an observer in motion. This is not a perceptual illusion. The events genuinely occur at different times in different reference frames. Time ordering for events separated by sufficient distance can flip depending on your state of motion. This fact has a consequence so strange it takes a moment to absorb. If an object could travel faster than light, some observers would see that object moving forward through time from sender to receiver. But other observers moving at different velocities would see the same object moving backward, through time arriving before it departed. This is not interpretation. It is a direct mathematical consequence of the relativity of simultaneity combined with faster-than-light motion. Now imagine using such a technology twice. You send a message from Earth to a distant station faster than light. From Earth's reference frame, the message travels forward in time, arriving after it was sent. The station receives the message and immediately sends a reply using the same faster-than-light mechanism. In certain reference frames, this reply travels backward through time relative to the original message's journey. The reply arrives at Earth before the original message was sent. You now know what the station will say before you ask the question. You could choose not to send the original message based on the reply you have already received. But if you do not send the message, the reply was never triggered. The reply cannot arrive. But you received it. The contradiction is irresolvable. Cause and effect have become tangled into a loop with no logical solution. These causal paradoxes are not philosophical curiosities. They represent actual contradictions in the structure of physical law. A universe where faster-than-light signaling is possible is a universe where the distinction between past and future dissolves, where effect can precede cause, where the ordered sequence of events that makes physics coherent, that makes science possible at all, ceases to function. The speed of light is not a traffic regulation imposed on an otherwise permissive universe. It is a causality preservation mechanism. It is the rate at which influence propagates through spacetime, and its universality is what ensures that cause always precedes effect for all observers everywhere always. This is what it means to say the barrier is structural rather than technological. Special relativity built this wall with mathematical precision. But 11 years after publishing Special Relativity, Einstein completed a far more ambitious theory, general relativity, and buried within its equations, waiting undisturbed for nearly 8 decades before anyone noticed, was something that appeared to offer a way through, not through the wall, around it. General relativity begins with a single unipiso radical that even Einstein struggled to fully accept its implications for years after he derived them. Spacetime is not a stage. In every physics that came before 1916, space and time provided the backdrop against which events occurred. The universe was a theater, and matter was the performance. Stars burned planets, orbited particles collided, and all of this happened within an arena that remained fundamentally passive, an infinite, unchanging geometric container that simply existed, providing coordinates, asking nothing, contributing nothing. Newton's absolute space and absolute time were not substances with properties. They were the emptiness in which substances with properties resided. They were the silence between the notes, not the music itself. Einstein erased this picture entirely. In general relativity, space and time are not a container for the universe. They are a participant in it. Mass and energy do not simply exist within spacetime. They shape it. They curve it. They warp its geometry in ways that determine how everything else moves. And the moving things in turn carry energy that further distorts the geometry around them. The universe is not matter performing on a stage. It is matter and geometry engaged in a continuous, mutual, dynamic conversation. To feel what this means, consider the simplest case, the Earth. Our planet has mass, and that mass curves the space-time around it. Not the space around it in the three-dimensional sense you might first imagine, but the four-dimensional geometry of space and time together. The curvature is subtle near a planet like Earth, but it is real and measurable. When you drop a stone, the stone does not fall because the Earth is pulling on it through some invisible force reaching across the empty space between them. The stone falls because the Earth's mass has curved the space-time in the region between your hand and the ground, and the stone is following the straightest possible path through that curved geometry, a path that leads inexorably toward the planet's center. The stone experiences no force in any meaningful local sense. From the stone's perspective, it is simply coasting, moving in a straight line through curved terrain. The curvature of the terrain is what produces what we call falling, what we call gravity. Not a push, not a pull, a geometric inevitability. This geometric interpretation of gravity has been tested with a precision that should inspire genuine awe. During solar eclipses, astronomers have measured the positions of stars whose light passes close to the sun. That light bends around the sun's mass exactly as curved spacetime predicts by an angle that Newton's gravity gets wrong and Einstein's geometry gets exactly right. Atomic clocks placed at different altitudes run at different rates because gravitational field strength varies with distance from Earth's center, and those variations warp the flow of time itself. The GPS satellites orbiting above us carry clocks that tick at measurably different rates than identical clocks on the surface, and the entire GPS system requires corrections based on general relativistic calculations down to nanosecond precision. Without those corrections, the system would accumulate position errors of several kilometers per day and become useless within hours. In 2015, 100 years after Einstein published the theory, the Laser Interferometer Gravitational Wave Observatory detected the first direct evidence of gravitational waves, ripples in spacetime geometry, itself propagating outward from two black holes that had spiraled together and merged over 1 billion light-years away. These waves stretched and compressed the physical distance between the observatory's mirrors by less than 1,000th the diameter of a proton. The measurement required instruments of almost incomprehensible sensitivity, and the signal matched Einstein's predictions with extraordinary fidelity. General relativity is not a speculative framework. It is one of the most precisely verified theories in the history of science. When it tells us something about the nature of spacetime, we should listen carefully. What it tells us in the context of our journey is something that changes everything. Spacetime is dynamic. It is not fixed. It bends, it stretches, it compresses, and it can do all of these things at rates entirely unconstrained by the speed of light. Consider what is happening to the universe right now as you read these words. The space between distant galaxies is expanding, not galaxies moving through space as we might imagine rockets moving through air. The space itself between them growing, the fabric stretching, carrying the galaxies apart as a rubber sheet carries dots drawn on its surface when the sheet is stretched. Edwin Hubble observed this in 1929, noticing that virtually every distant galaxy showed a redshift in its light. Its wavelength stretched longer, its frequency reduced, consistent with the galaxy receding from us. The more distant the galaxy, the greater the redshift, the faster the recession. What Hubble could not fully appreciate, and what took cosmologists decades more to absorb, is that the recession velocities of the most distant galaxies exceed the speed of light. Right now, galaxies at the edge of the observable universe are receding from us at approximately 2 to 3 times the speed of light. Their distance from us grows faster than any signal we could ever send could possibly travel. And this violates nothing. No physical law is broken, no cosmic rule is bent, because those galaxies are not moving through space at superluminal velocities. They are not streaking outward like projectiles launched at impossible speeds. The space between us and them is simply growing, expanding, and when you integrate that expansion across billions of light-years of intervening distance, the cumulative recession velocity exceeds 300,000 kilometers per second without any individual piece of space doing anything. Dramatic. The ant and the balloon. Imagine an ant walking across the surface of a balloon that someone is slowly inflating. The ant moves at ant speed a few centimeters per minute, but 2 points on the balloon surface might separate from each other, at any rate depending on how quickly the balloon expands. If you inflate the balloon fast enough, 2 distant points can separate faster than the ant could ever walk, even though the ant is obeying its speed limit faithfully, and the balloon is not violating any rule of balloon physics. The expansion of the balloon surface is simply not subject to the ant's personal velocity constraint. The galaxies are the dots. The expansion of space is the balloon. The ant is light, the fastest thing that can move through space. Light obeys its speed limit exactly and always, but space itself carries things at rates beyond that limit, and in doing so violates nothing. This distinction between moving through space and being carried by expanding or contracting space sounds like a technicality. It is not. It is the most important conceptual distinction in the entire story we are telling tonight. It is the crack in the wall. The fine line between what special relativity absolutely forbids and what general relativity quietly permits. Special relativity is iron in its prohibition of objects moving through space faster than light. But general relativity introduces a category of motion that special relativity simply does not address the motion of spacetime itself. Spacetime can do things that objects within spacetime cannot. This was understood for decades as an interesting cosmological fact. A curious feature of the universe's large-scale evolution, relevant to discussions of galactic recession and cosmic inflation and the ultimate fate of the observable universe, but not obviously relevant to spacecraft or transportation or the dream of reaching the stars. The cosmic inflation that occurred in the first fraction of a second after the Big Bang provides the most dramatic example of this distinction in action. In approximately 10 to the minus 32 seconds, a decimal point, followed by 31 zeros and then a 1, the observable universe expanded from a region smaller than a proton to a volume roughly the size of a grapefruit. Every point in space separated from every other point at velocities so far beyond the speed of light that no comparison makes intuitive sense. The expansion factor was something like 10 to the 26th power, and nothing moved faster than light. Nothing in the universe was moving through space at superluminal velocities during inflation. Space itself was expanding. The distinction preserves every consequence of special relativity, while permitting the universe to grow in ways that appear impossible from the perspective of special relativity alone. The physicist Alan Guth proposed this inflationary model in 1980 to solve several puzzling features of the observable universe: why it looks so uniform in all directions, why its geometry appears so flat, why the cosmic microwave background radiation has the same temperature across regions of sky that should never have been in causal contact. Inflation solved these problems elegantly by proposing that the entire observable universe originated in a tiny region that was in causal contact before expanding stupendously fast. The regions that look similar today look similar because they were once neighbors, before space-time itself carried them to opposite ends of what would become our observable universe. Guth's inflation was not science fiction. It left observable signatures in the distribution of matter throughout the universe and in the subtle temperature variations of the cosmic microwave background radiation that the WMAP and Planck satellites later measured with exquisite precision. The signatures are there. Inflation, or something very much like it, almost certainly happened. The universe is in a very real sense powered by the dynamics of space-time geometry itself, not merely by the motion of matter through a passive arena. Space-time is active, it participates, it expands at rates beyond light speed, and did so most dramatically at the universe's very beginning, which brings us to the question that changed theoretical physics in 1994. If space can expand faster than light, carrying galaxies apart at superluminal recession velocities without violating any physical law, if the universe itself can do exactly what special relativity forbids matter from doing, might it be possible to engineer a local region of space-time geometry that moves through the broader universe at faster than light speed, not as a cosmological accident of universal expansion, but as a deliberate, controlled configuration? Could you create a bubble? Could you construct through some arrangement of mass and energy a localized region of flat spacetime, surrounded by warped geometry that propagates through the universe at arbitrary velocity, carrying whatever sits inside it to distant destinations in arbitrarily short times, while everything within that region obeys all the local speed limits without exception? The answer requires understanding how Einstein's field equations actually work, not just what they predict in familiar circumstances, but what they permit when you ask them questions they were not originally designed to answer. Einstein's field equations relate two mathematical objects. On one side, a description of spacetime curvature, a tensor, encoding how distances and durations relate to each other throughout the geometry, how the fabric of space and time is bent and twisted by whatever mass and energy resides within it. On the other side, a description of that mass and energy itself, another tensor specifying where matter concentrates, how energy flows, what forces act where. The equation states that these two objects are proportional, linked by constants that include the speed of light and Newton's gravitational constant. The standard way to use this equation is straightforward. You specify the distribution of matter and energy, the mass of a star, the density of a neutron star, the properties of a collapsing object, and you solve for the resulting spacetime curvature. This is how we calculate the geometry around black holes, how we predict the behavior of gravitational waves, how we model the expanding universe. You know the stuff, and the equations tell you the shape. Miguel Alcubierre, a Mexican physicist working at the University of Wales in 1994, decided to run the equation in reverse. Instead of starting with known matter and solving for geometry, he started with a desired geometry and solved for the matter that would produce it. The geometry he desired was simple to describe and extraordinary in its implications: a bubble of perfectly flat spacetime moving through the broader universe at faster than light speed. Inside the bubble, physics operates completely normally. Space is uncurved. An observer inside experiences no acceleration, no unusual forces, no time dilation beyond whatever they started with. The laws of physics function exactly as they do anywhere else in undistorted spacetime. Nothing inside the bubble moves faster than light relative to its local surroundings. But the bubble itself, embedded in the surrounding spacetime, carried by a wave of geometry, propagating outward, moves through the cosmos at velocities unconstrained by the light barrier. He wrote down the metric, the mathematical description of this spacetime geometry. He verified that it satisfied Einstein's field equations. It did exactly without approximation. The warp drive metric is not a guess or an approximation. It is an exact solution to general relativity, as rigorous and mathematically legitimate as the Schwarzschild metric describing black holes, or the Friedmann metric describing the expanding universe. The universe's most precise theory of gravity and spacetime looked at Alcubierre's geometry and accepted it without objection. The mathematics allowed it. But then Alcubierre did the second calculation. He plugged his metric back into the field equations and asked what matter distribution would produce this geometry. What kind of physical stuff arranged in what configuration would curve spacetime in the precise way his bubble required? The answer arrived with the force of a door slamming shut, not the energetic slamming of an engineering problem discovering its difficulty, something quieter and more absolute. The sound of a universe declining to cooperate in terms that left no room for negotiation. The warp bubble requires negative energy density, not low energy, not zero energy, negative energy, a quantity of energy less than the energy of empty vacuum. Matter possessing gravitational properties opposite to everything that has ever been directly observed. Not matter that attracts, but matter that repels. Not matter that focuses geodesics, the paths objects follow through curved spacetime, but matter that defocuses them, pushing them apart with gravitational effects, running exactly opposite to every form of mass and energy we have ever measured. The universe permits the geometry. It cannot be produced by anything the universe provides. And this is where the story becomes genuinely strange, because negative energy is not entirely a theoretical fiction. Quantum mechanics has something to say about it, something that initially appeared to offer a sliver of hope before the implications were worked out fully, and the sliver of hope was revealed to be an illusion measured in the difference between what the universe can provide and what the warp drive needs. The gap, when you calculate it, is almost impossible to comprehend. But that is the next layer of the story. The first layer has already taught us something profound. The mathematics of general relativity permits configurations that special relativity would seem to forbid. The equations accept solutions where effective faster-than-light travel occurs without any local speed limit being violated. The geometry of spacetime offers an apparent loophole through the wall that Newtonian intuition and special relativistic physics built around our cosmic ambitions. The universe says, here is the geometry you want. It is mathematically legitimate. It does not contradict me. And then it says, now let me show you what it would take to build it. 1414, Claude responded. Picture a wave moving across the surface of the ocean. Picture a wave moving across the surface of the ocean. The water does not travel with the wave. This is the thing most people misunderstand when they watch the sea. The wave moves forward, crossing enormous distances, carrying energy from the storm that created it thousands of miles away to the shore where it finally breaks. but the individual water molecules beneath the wave's surface move in roughly circular patterns, rising as the wave approaches, falling as it passes, returning nearly to where they started once the wave has gone. A seabird sitting on the surface bobs up and down. It does not travel with the wave. The wave passes beneath it. What moves is the shape, the pattern, the geometry of the water's surface propagating forward through a medium that itself stays largely in place. This distinction between the motion of a wave and the motion of the medium through which it travels is not a metaphor I am using loosely. It is the precise physical analogy for how a warp drive would function translated from water to spacetime. What Alcubierre proposed was not a spacecraft that moves through space faster than light. It was a wave in the geometry of spacetime itself, carrying a region of flat space forward through the cosmos, the way an ocean wave carries its crest forward through water, while the thing inside that region, the spacecraft, the passengers, the air they breathe, remains essentially stationary with respect to its immediate surroundings. To understand the geometry more precisely, you need to hold two images in your mind simultaneously. The first image is space contracting. Imagine the region of spacetime directly ahead of the warp bubble. In Alcubierre's metric, this region undergoes compression. Distances in the direction of travel shrink. A star that sits 100 light-years ahead in normal, undistorted space would within the compressed region ahead of the bubble be effectively much closer, the intervening distance squeezed down as if someone had taken the fabric of space and gathered it like a curtain being drawn. The destination does not move in any absolute sense, but the space between the bubble and the destination has been compressed, and compressed space means reduced distance, and reduced distance means reduced travel time regardless of velocity. The second image is space expanding behind. Simultaneously, the region of spacetime directly behind the warp bubble undergoes expansion. Distances in the backward direction stretch. The starting point recedes rapidly, not because the spacecraft has moved away from it, but because the space between the spacecraft's current position and its origin has been stretched outward. The origin grows more distant, not through motion, but through the geometry of the spacetime region trailing behind the bubble. Now combine these two images. Space contracting ahead, space expanding behind. A region of flat, undistorted spacetime sandwiched between these two zones of intense curvature. And the spacecraft sitting quietly in the flat region stationary, with respect to the local geometry, experiencing no acceleration, feeling nothing unusual, while the entire configuration, the contracting front, the flat middle, the expanding back, propagates through the broader universe like a wave. The spacecraft is the seabird. The warp bubble is the ocean wave. The seabird does not move through the water. The wave carries the seabird forward. Alcubierre described a more mechanical analogy that has the virtue of being precise. Imagine an airport moving walkway. You stand still on its surface. Your feet do not move relative to the belt beneath them, but the belt carries you forward through the terminal at whatever speed the mechanism provides. Now imagine a walkway with no speed limit, one that could move at 1,000 times walking pace, or 1,000,000 times, or any arbitrary velocity. You still stand motionless on its surface. You still obey your personal speed limit relative to the belt, but the belt transports you at rates far beyond what your legs could ever achieve. The warp bubble is this walkway, but the belt is spacetime itself. The spacecraft never moves faster than light relative to the local spacetime inside the bubble. The spacetime inside the bubble never moves faster than light relative to the spacetime immediately adjacent to it. But the cumulative effect of space contracting ahead and expanding behind produces a wavefront that propagates through the broader universe at superluminal velocity. An observer watching from a distant star would see the bubble approaching faster than any light signal could precede it. The bubble would arrive before any announcement of its departure. This is what distinguishes the warp drive concept from naive, faster-than-light proposals. A spacecraft with a very powerful engine is still a spacecraft moving through space. Special relativity applies to it completely and absolutely, and the energy barrier that climbs toward infinity as velocity approaches light speed applies with full force. The warp drive is not that spacecraft. It is not moving through space. It is moving space. And the rules governing how fast space itself can move are different from the rules governing how fast objects can move through space. The contraction ahead of the bubble has a further implication worth dwelling on. When space is compressed in the direction of travel, the effective distance to the destination shrinks. A journey of 4 light-years to Alpha Centauri might, within a sufficiently compressed region of space, involve traversing the equivalent of only a few kilometers of actual geometric distance. You are not traveling 4 light-years. You are traveling a much shorter distance through highly compressed space that happens to connect your origin to a destination that was originally 4 light-years away in normal geometry. Think of it this way. Imagine drawing 2 dots on a piece of paper placed far apart. Now fold the paper so the dots nearly touch. You have not moved either dot, but the distance between them measured along the paper's surface has become negligible. The destination is now close, not because it moved, but because the medium connecting you to it was rearranged. The warp bubble does something analogous in 3 dimensions with the geometry of spacetime. It does not violate the rule that you cannot travel faster than light through space. It rearranges the space so that the journey measured locally is trivially short. The passengers aboard a vessel inside such a bubble would experience nothing dramatic during travel. No crushing acceleration. No time dilation beyond whatever relativistic effects they accumulated from their initial boost into the bubble. No unusual forces, no distorted perceptions of time, no physiological stress. They would sit in their ship, drink their coffee, look at their instruments, and experience a perfectly ordinary passage of time. Their clocks would tick at normal rates. The laws of physics would behave exactly as they do anywhere else in flat spacetime. Then the bubble would dissolve at the destination. The spacecraft would emerge, and an external observer watching from that destination would see the vessel arriving in a time that seemed impossibly short days or hours, for a journey that should have taken years with no violation of any law of physics having occurred. Within any local reference frame, the mathematics is exact, the geometry is rigorous. Einstein's field equations accept this solution with complete mathematical validity, the same validity they extend to black holes and gravitational waves and the expanding universe. The warp drive metric is not an approximation or a thought experiment dressed up as physics. It is a genuine solution to the governing equations of the most precisely tested theory of gravity in scientific history. And then Alcubierre asked the second question, what would it actually take to create this geometry? Einstein's field equations work in both directions. You can specify geometry and solve for the required energy distribution, just as you can specify energy and solve for the resulting geometry. Alcubierre ran the calculation in reverse, asking what matter configuration would produce the space-time curvature his metric described. The result was unambiguous and immediately devastating. The warp bubble requires a shell of exotic matter surrounding the flat interior region. Exotic matter is a technical term in physics for matter possessing negative energy density, energy less than the vacuum of empty space. In ordinary physics, empty space has 0 energy density, and all known forms of matter and energy have positive energy density above this baseline. Exotic matter would have negative energy density falling below the vacuum baseline, possessing what amounts to less than nothing in energetic terms. This matters for the geometry because of how energy curves spacetime. Ordinary positive energy density curves spacetime in a way that causes geodesics, the paths that freely moving objects and light rays follow to converge toward each other. This is gravitational attraction. Mass pulls things toward it. Light bends around massive objects. The focusing of geodesics by positive energy is one of the most fundamental and well-confirmed features of general relativity. The warp bubble requires the opposite. The region ahead of the flat interior must defocus geodesics, push them apart, compress space in the direction of travel rather than drawing things together. Only negative energy density can accomplish this. Only matter that curves spacetime in the opposite direction from all observed matter can produce the gravitational repulsion the bubble's geometry demands. Negative energy is not entirely unknown to physics. This is where the small sliver of hope entered the story and where its inadequacy becomes apparent upon careful examination. Quantum mechanics predicts that the vacuum of empty space is not truly empty. It seethes with quantum fluctuations, virtual particle pairs continuously appearing and annihilating on timescales so brief they cannot be directly observed. These fluctuations have energy, and in certain configurations they can produce small regions where the local energy density falls below the vacuum baseline genuinely negative energy density, however slight. The Casimir effect provides the clearest experimental demonstration of this phenomenon. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged parallel metal plates, placed extremely close together in a vacuum, would experience an attractive force pushing them together. The mechanism involves quantum vacuum fluctuations. Between the plates, the geometry restricts which wavelengths of vacuum fluctuations can exist. Only fluctuations with wavelengths that fit between the plates are permitted. Outside the plates, all wavelengths can exist. This asymmetry creates a slight difference in the quantum vacuum energy between the interior and exterior regions. The interior has slightly less vacuum energy than the exterior. The interior, in precise technical terms, has slightly negative energy density relative to the surrounding vacuum. The plates are pushed together by this energy difference. The force is real. It has been measured experimentally with considerable precision matching theoretical predictions. The Casimir effect is not theoretical speculation. It is observed physics. When physicists first worked through this, some allowed themselves a moment of optimism. Negative energy density exists. The universe permits it, at least at small scales. Perhaps a sufficiently clever arrangement of quantum systems could produce the negative energy required for a warp bubble. Perhaps the Casimir effect scaled up or configured appropriately could provide what the geometry demands. That optimism lasted precisely as long as it took to compare the numbers. The Casimir effect between parallel plates, separated by 1 micrometer, 1/1,000,000th of a meter, roughly 100 times smaller than the width of a human hair, produces a negative energy density of approximately 10 to the -3 joules per cubic meter, 1,000th of a joule per cubic meter. Alcubierre's original calculations for the energy required by his warp bubble, when converted to mass-energy equivalents through Einstein's equation relating energy and mass, suggested a requirement on the order of the mass energy of Jupiter. Subsequent calculations revised this to stellar masses. The most optimistic later estimates incorporating geometric refinements that reduced energy requirements as dramatically as theoretically possible still arrived at numbers ranging from the mass equivalent of a large asteroid to the mass equivalent of a mountain, depending on assumptions about bubble size and wall thickness. Even taking the most optimistic estimate, a mountain's worth of mass energy in negative form, and comparing it to what the Casimir effect provides, the gap is approximately 30 orders of magnitude. That is a 10 followed by 30 zeros. That is the difference between a single atom and a billion trillion stars. That is not an engineering gap awaiting better technology. That is not a factor of 10 requiring improved efficiency, or a factor of 1,000 requiring a breakthrough in materials science. 30 orders of magnitude is a statement about the structure of reality. It says that the quantum effects which produce negative energy operate in a regime so distant from what the warp bubble requires that no conceivable scaling or combination of known physics bridges the distance. But the gap in magnitude is not even the deepest problem. The quantum inequalities derived by physicist Lawrence Ford and his collaborator Thomas Roman, beginning in the 1970s, and refined over subsequent decades, impose a constraint on negative energy that operates independently of scale. These inequalities are mathematical theorems about what quantum mechanics permits, and they state, with the force of rigorous proof, that negative energy density cannot be sustained arbitrarily. The principle is this: negative energy must be paid back. If you create a region of negative energy density, the universe demands compensation in the form of positive energy appearing nearby, and it demands this compensation quickly. The more negative the energy density you create, the faster the positive energy must appear to balance it. The larger the spatial region of negative energy, the more total positive energy must compensate. The longer you try to maintain negative energy in a given region, the more steeply the requirements grow. Imagine borrowing money from a lender whose interest rate increases as a function of how much you borrow, and how long you hold the loan with no upper limit on either the interest rate or the speed at which the balance comes due. You can borrow small amounts briefly. You cannot borrow large amounts for extended periods without the debt growing faster than you could ever repay it. The quantum vacuum operates on analogous principles with energy. You can create tiny regions of negative energy for tiny fractions of a second. You cannot create macroscopic regions of sustained negative energy because the compensation requirements become overwhelming before the region can achieve any useful size or duration. A warp bubble requires negative energy distributed across a macroscopic shell surrounding the spacecraft, sustained for the entire duration of travel, potentially hours or days. The quantum inequalities make this configuration not merely difficult but fundamentally incompatible with what quantum mechanics permits. Nature will not lend you negative energy on those terms. The loan officer has examined the application and declined. The mathematics allows the geometry. The physics forbids the energy source that would produce it. This is the first layer of the defense. But notice something important about how the problem presents itself. The constraint is not arbitrary. The quantum inequalities protecting against macroscopic negative energy are not ad hoc rules added to physics, specifically to prevent warp drives. They emerge from the foundational structure of quantum mechanics, from the same principles that correctly predict the Casimir effect, the Hawking radiation of black holes, the behavior of quantum fields in curved spacetime. They are consequences of deep physical principles that connect to everything else we understand about matter and energy. The universe is not targeting warp drives specifically. It is enforcing principles that govern all energy everywhere, and those principles happen to foreclose the possibility of the energy configuration the warp bubble needs. This pattern, general principles of physics operating throughout the universe for entirely independent reasons, converging to prevent faster-than-light configurations, will repeat. It is the signature of a constraint that is structural rather than incidental. When multiple independent principles all point toward the same prohibition, the prohibition is not accidental. It is telling you something about the architecture of physical law. Yet the theoretical exploration did not end with the exotic matter problem. Physics does not surrender to a single barrier, however formidable. The decades following Alcubierre's paper saw persistent effort to find ways around the exotic matter requirement, to construct warp-like geometries, using only positive energy to discover whether the universe's prohibition on negative energy in macroscopic quantities truly foreclosed all possible paths to effective superluminal travel. What those efforts found was not a way around the barrier. They found that removing the barrier exposed something worse beneath it, and then something worse beneath that. The resistance is not a single wall. It is a sequence of walls, each one becoming visible only when you have broken through or imagined breaking through the one in front of it. And behind each wall, the universe waits with the same answer it has given from the beginning. The math allows it. The universe resists it. Suppose for a moment that the exotic matter problem was solved. Suppose some future physics, some discovery we cannot yet imagine, provided a mechanism for producing and sustaining negative energy density at macroscopic scales. Suppose the quantum inequalities turned out to have exceptions we have not yet found. Or suppose a modified theory of gravity permitted warp-like geometries with positive energy alone. Suppose generously that the first and most obvious barrier simply fell. What would you have? You would have a bubble of flat space-time propagating through the cosmos at superluminal velocity, a geometric wave carrying its contents toward a destination light-years away. The engineering triumph of human history, realized at last after centuries of dreaming. And you would have no way to steer it, no way to stop it, no way to communicate with anything outside it, no way to adjust your course if something appeared in your path, no way to know whether you had arrived until the bubble dissolved, at which point whatever adjustment you might have wanted to make would already be irrelevant. These are not engineering inconveniences awaiting clever solutions. They are consequences of the bubble's geometry itself, emerging from the same mathematical structure that produces the superluminal propagation. The property that allows the bubble to move faster than light is precisely the property that severs its interior from any possibility of control. You cannot have the speed without the isolation. The physics that enables one forbids the other with the same breath. To understand why, you need to think carefully about what a horizon means. The word horizon conjures a visual boundary, the line where the Earth's surface curves away from your line of sight, beyond which you cannot see because the geometry of the planet's surface prevents it. But in physics, a horizon has a more precise and more absolute meaning. A horizon is a boundary in space-time, beyond which no signal, no influence, no information of any kind can propagate in a given direction. It is not a limitation of your instruments. It is a feature of the causal structure of space-time that no technology can circumvent because signals travel at light speed and some regions of space-time are structured so that light speed is not sufficient to cross the gap. Black holes have horizons. Once you cross the event horizon of a black hole, no signal you emit can escape back to the external universe. Light you shine outward moves at 300,000 kilometers per second, but the curvature of spacetime near the singularity is so extreme that every path light can travel leads deeper into the black hole rather than back out. The horizon is not a wall you can push through with enough force. It is a region where the geometry of spacetime has been arranged so that outward motion is geometrically impossible as moving backward through time in flat spacetime. A superluminal warp bubble creates a horizon with similar absoluteness. Consider a spacecraft sitting inside the flat region of the bubble, attempting to send a signal to the bubble's leading edge, the forward boundary where space is contracting most intensely. This signal, even traveling at the speed of light, must traverse the distance between the spacecraft and the forward boundary. But the forward boundary is moving away from the spacecraft at superluminal velocity. The signal races toward the boundary at 300,000 kilometers per second. The boundary recedes faster. The signal can never arrive. The spacecraft is causally disconnected from the forward region of its own bubble. Signals from the interior cannot reach the exterior ahead. Instructions cannot be transmitted to whatever mechanism maintains the contracting space in front. Course corrections cannot be sent to the geometry that determines the bubble's trajectory. The spacecraft and everything inside it is informationally isolated from the very part of the bubble that determines where it is going and how fast it is getting there. This is not a malfunction. This is the warp bubble working exactly as intended. The same geometry that compresses space ahead of the bubble, enabling the superluminal propagation, also ensures that no light signal from the interior can outrace the bubble's forward boundary. The compression and the isolation are not separate features that might be independently adjusted. They are two aspects of the same geometric configuration. Turn up the compression for more speed, and the isolation becomes more complete. Reduce the isolation to allow communication, and you reduce the compression, slowing the bubble, eventually bringing it below light speed, where the horizon structure changes and control becomes theoretically possible again. For a superluminal bubble, control is not merely difficult. It is geometrically forbidden by the causal structure of the spacetime configuration. Now consider stopping. When the spacecraft reaches its destination, or what it believes to be its destination, since it has no way to confirm its position while inside the bubble, how does it halt? To stop a warp bubble, the geometry must be modified. The contraction ahead must be reduced, then eliminated. The expansion behind must be similarly dissipated. The bubble must gradually dissolve from a propagating wave back into flat spacetime. This requires manipulating the exotic matter distribution that generates the geometry, adjusting it in ways that smoothly decelerate the bubble. But the exotic matter distribution is in the bubble wall. The bubble wall is the region the spacecraft cannot communicate with. The spacecraft cannot reach out to the geometry surrounding it and instruct it to change. The bubble will continue propagating at whatever velocity it was set to when it formed, carrying its contents past the destination, through the destination's solar system, across the destination's galaxy forever, unless some mechanism operating from outside the bubble intervenes to stop it. What mechanism? Who would position themselves at the destination across multiple light-years of interstellar space to intercept a superluminal bubble whose arrival they cannot predict because the bubble travels faster than any announcement of its departure? How would they stop it? By what means does an external agent dissolve a warp bubble without access to the exotic matter, generating it without being able to communicate with the occupants inside. Each question reveals the next. The practical impossibilities compound into something that feels less like an engineering challenge and more like a fundamental misalignment between what the technology would require and what the physics permits. Some theorists have proposed that the trajectory could be pre-programmed. The bubble geometry could be designed in advance to automatically dissolve at a specific location, the destination coordinates encoded into the initial configuration. The bubble becomes a ballistic missile, rather than a steerable vehicle aimed at a target, fired and expected to arrive without further guidance. The objections to this approach emerge immediately upon examination. Stars move, planets orbit. The Alpha Centauri system, our nearest stellar neighbor, contains at least one known planet orbiting within the habitable zone of its star. That planet has an orbital period of approximately 11 days. A journey to Alpha Centauri, even at 10 times light speed, would take 5 months. In 5 months, the planet completes roughly 14 full orbits. A pre-programmed trajectory aimed at the planet's position when the bubble departed would arrive at empty space, the planet having moved almost 100 million kilometers from its calculated position. You could correct for this, of course, calculate the orbital mechanics, predict where the planet will be at arrival, aim for that future position, but this requires knowing the journey, time with precision, which requires knowing the bubble velocity with precision, which requires real-time telemetry from a bubble that cannot send signals outward, all solved in advance, using calculations whose accuracy must be maintained across interstellar distances and months of travel. And this is only the simplest obstacle. Interstellar space is not empty. It contains gas and dust at average densities of roughly 1 atom per cubic centimeter. Magnetic fields thread through the galaxy in complex patterns that are incompletely mapped. Rogue planetesimals drift through the void undetected. Comets traveling on long elliptical orbits appear in unexpected places. Any of these could affect a journey. None can be anticipated in a pre-programmed trajectory calculated from Earth. The collision question raises its own disturbing calculations. As a superluminal warp bubble sweeps through interstellar space, it encounters this sparse but non-zero distribution of matter and radiation. What happens to that material when it contacts the bubble boundary? Theoretical analysis suggests 2 possible outcomes, and neither is welcoming. In the first scenario, material ahead of the bubble is swept up by the contracting space at the leading edge. As space compresses in front of the bubble, matter distributed through that space is compressed along with it, accumulating at the forward boundary, being pushed ahead of the bubble like snow, accumulating ahead of a plow. Over the course of a journey spanning light years, the total accumulated material could be substantial: gas, dust, cosmic ray particles, interstellar ice, all compressed into a shell at the bubble's leading edge and heated to extreme temperatures by the compression. By the time the bubble arrives at its destination and dissolves, that shell of compressed superheated material would be released at once in the direction of travel toward whatever the bubble was heading for. The energy in this compressed shell grows with journey distance. For a trip spanning several light years, the accumulated material and its kinetic and thermal energy could exceed the yield of nuclear weapons by enormous factors. Arriving at a destination would mean detonating an astrophysical explosion in its vicinity. In the second scenario, material is deflected around the bubble rather than accumulated ahead of it. The extreme spacetime curvature at the bubble boundary might redirect incoming matter like water, flowing around a moving object, parting the interstellar medium and closing it behind the bubble's passage. This sounds more benign, but matter accelerated to near-light velocities around the bubble boundary produces intense radiation, gamma rays, high-energy particles, electromagnetic emissions that would irradiate everything along the bubble's path with lethal intensity. Neither scenario permits safe travel through occupied space. Both impose severe consequences on the destination and on anything the bubble passes near. A warp drive is under either analysis a weapon of extraordinary destructive power, regardless of the intentions of those operating it. The same geometry that enables the travel creates the danger. They cannot be separated. This observation belongs to the same pattern we have been watching build. The property that makes the warp bubble useful produces a consequence that makes it dangerous. Speed and isolation, propagation and uncontrollability, arrival and destruction. The desirable feature and its unacceptable consequence are not separate problems that might be solved independently. They are two expressions of a single underlying geometric reality. But all of these concerns, navigation control, stopping collision, are, in some sense, practical concerns. Engineering problems of sufficient severity that they might prove insurmountable, but problems that do not strike at the logical foundations of physics. There is a deeper objection to superluminal travel that operates at precisely that foundational level. An objection that does not ask whether we can solve the engineering, but whether the physics itself permits the logical consequences of success. This is the causality problem. You encountered it earlier in the story, in the context of special relativity, and the prohibition against faster-than-light signals. The argument was simple. If you can send information faster than light, some observers will see that information traveling backward through time. And if information can travel backward through time, causal loops become possible. Causes can follow effects. The past can be influenced by the future. The logical structure that makes physics coherent dissolves. The warp drive appeared to sidestep this objection through its clever use of local spacetime geometry. Nothing inside the bubble moves faster than light relative to its local surroundings. The bubble propagates through spacetime geometry, not through space. Surely this distinction exempts it from the causality concerns that plague naive faster-than-light proposals. It does not. The relevant question is not what velocity is measured locally within the bubble. The relevant question is what happens when you compare the space-time positions of the departure event and the arrival event. If the bubble enables travel between 2 points in less time than light would require to make the same journey through normal space, then from certain reference frames in relative motion to the bubble's trajectory, the arrival occurs before the departure. The arrival is in the past of the departure measured from those reference frames. This is not a matter of local versus distant measurements. It is a consequence of the relativity of simultaneity that Einstein established in 1905. Observers moving at different velocities disagree about the time ordering of spatially separated events. For events connected by a superluminal path, any superluminal path regardless of the mechanism producing it, some observers will see the arrival preceding the departure. This is mathematical certainty, not speculation. Now use a second warp bubble for the return journey. You depart from Earth in a warp bubble and arrive at Alpha Centauri in what your clocks measure as 2 days, having covered 4 light years. You then board a second warp bubble and return to Earth. Depending on the velocities involved on the reference frames of the observers, on the specific space-time geometry of each journey, you can arrange the round trip so that you arrive back on Earth before you left. Not just before the light of your departure could have reached Earth. Before you departed, you return to a time before you left. You meet yourself preparing to enter the first warp bubble. You could tell yourself what you found at Alpha Centauri. You could warn yourself not to go. You could, in principle, prevent yourself from making the journey that brought you back in time to have this conversation. These paradoxes are not puzzles for philosophers to enjoy at a comfortable distance from physics. They represent genuine logical contradictions that, if permitted, would make physical prediction impossible. A universe where causes can follow effects is a universe where the state of the present does not uniquely determine the future, where the past is as uncertain as the future, where physical law loses its meaning because the sequence of events it is meant to describe has no definite ordering. The physicist Stephen Hawking took these concerns seriously enough to propose in 1992 what he called the chronology protection conjecture. The laws of physics, Hawking suggested, conspire to prevent the formation of closed time-like curves, paths through spacetime that loop back to their own past. Not because any single law explicitly forbids such curves, but because multiple physical mechanisms operating through distinct channels collectively destabilize any configuration approaching causal violation before it can be completed. The conjecture has never been proven as a mathematical theorem. The complete theory of quantum gravity needed for such a proof does not yet exist, but 3 decades of theoretical investigation have accumulated substantial evidence in its favor. Every time physicists have carefully analyzed a proposed mechanism for creating closed time-like curves, rotating black holes, traversable wormholes, advanced configurations of exotic matter, superluminal warp drives, quantum effects near the region where causality would be violated have proven catastrophically destabilizing. The mechanism operates through the behavior of quantum fields in curved spacetime. Near any region where a closed time-like curve would form, quantum vacuum fluctuations become amplified. The virtual particles that normally hover at the threshold of detectability, appearing and annihilating too quickly to have macroscopic effects, become enhanced by the unusual spacetime geometry into real particle production of increasing intensity. The energy density of this particle creation diverges, grows without bound, precisely at the boundary where the causal loop would close. This diverging energy density would destroy the spacetime configuration that was approaching causal violation. The warp bubble, on a trajectory that would enable causality-violating round trips, would encounter this catastrophic quantum back reaction before completing the journey. The bubble does not merely slow down or become unstable. It is obliterated by the quantum energy density that the universe generates in response to the threat to its causal structure. The universe in this picture does not passively permit configurations that would violate causality and then suffer the logical consequences. It actively destroys them before they can complete. The quantum vacuum functions as an enforcement mechanism, a physical implementation of the logical requirement that causality must be preserved, generating the energy needed to eliminate causal violations at precisely the moments they would otherwise occur. Some physicists find this picture too convenient, too neat, suspiciously well designed to produce the desired outcome. They note that the divergence of quantum energy near causal horizons has been demonstrated in semi-classical calculations, approximations that treat spacetime geometry classically, while treating matter fields quantum mechanically, but not in a complete quantum gravitational framework. The full calculation requiring a theory of quantum gravity we do not yet possess might produce different results. This is a legitimate concern. Our understanding of quantum gravity is incomplete, and incomplete theories can produce artifacts that disappear in more complete treatments. The chronology protection conjecture remains a conjecture rather than a theorem for precisely this reason. But notice the direction in which uncertainty cuts. We do not know whether quantum gravity would make causality protection more strict or less strict than semi-classical calculations suggest. But every time physics has been extended into new regimes, quantum mechanics extending classical physics, relativistic quantum field theory extending non-relativistic quantum mechanics, string theory attempting to extend quantum field theory, the extensions have consistently proven more restrictive, not less. New physics has never in the history of science revealed that previously forbidden configurations were actually permitted all along. It has repeatedly revealed that previously permitted configurations were actually forbidden by more fundamental principles. There is no guarantee this pattern will continue, but it is a pattern worth noting when evaluating how much confidence to place in the hope that quantum gravity might rescue warp drives from chronology protection. The 4 barriers examined now: exotic matter requirements, navigation, impossibility, collision consequences, and causality violation are not 4 versions of the same problem. They are 4 distinct physical mechanisms, each independently capable of forbidding practical warp travel, each emerging from different branches of physics, each supported by different theoretical foundations. Exotic matter requirements emerge from the focusing theorems of general relativity and the quantum inequality constraints on negative energy. Navigation impossibility emerges from the horizon structure of superluminal spacetime geometries. Collision consequences emerge from the dynamics of matter interacting with extreme spacetime curvature. Causality violation emerges from the relativity of simultaneity and the quantum mechanical response to closed time-like curves. Remove any one of them. Suppose exotic matter somehow becomes available. Suppose navigation problems are somehow circumvented Suppose collision dynamics somehow spare the destination and the others remain. You have not solved the problem. You have solved one instance of a constraint that the universe enforces through multiple independent channels. This is not coincidence. This is architecture. The cosmic speed limit is not protected by a single barrier that a sufficiently clever theory might eventually undermine. It is protected by an interlocking network of constraints, each one holding the others in place, each one emerging from principles so fundamental that modifying them would require modifying the basic structure of physical law throughout the universe. Pull out one constraint and the others shift to fill the gap. The defense is redundant in the way that living systems are redundant not through repetition of the same mechanism, but through multiple independent mechanisms, all converging on the same function. What does it mean that the universe is structured this way? That question will carry us into the final chapters of this story. But first we must examine the most recent theoretical proposals, the work of the past decade that generated headlines and genuine excitement by claiming to find warp geometries requiring no exotic matter at all. These proposals deserve careful examination not because they succeed, but because the manner of their failure reveals something important about the relationship between mathematical permission and physical reality that we have not yet fully articulated. The math allows it. The universe resists it. We are about to see just how deep that resistance goes. In 2021, a paper appeared that moved through the physics community with unusual speed. Eric Lentz, a physicist at the University of Göttingen, published a theoretical analysis claiming to have constructed a warp drive solution using only positive energy, ordinary matter, and energy of the kind that fills our observable universe, subject to all the standard energy conditions that physicists use to characterize physically reasonable matter distributions. No exotic matter, no negative energy density, no violation of the quantum inequalities that Ford and Roman had established as fundamental constraints on what the vacuum could provide. The headlines were immediate. Warp drive without exotic matter. The barrier that had stopped the field for nearly 3 decades, apparently circumvented. Several major science publications ran stories suggesting that the primary obstacle to faster-than-light travel had been removed. The excitement was genuine. Physicists who had studied the field for years found themselves rereading the paper carefully, looking for the error, wondering whether something fundamental had changed. Something had changed, but not in the direction the headlines suggested. Lentz had found a new class of solutions to Einstein's field equations, soliton configurations, self-reinforcing geometric structures that maintain their shape while propagating analogous to certain types of waves in fluid dynamics that travel without dispersing because they're non-linear. Dynamics precisely balance the tendency to spread. These solitons possessed, within the shell surrounding the flat interior region, distributions of positive energy density that satisfied the classical energy conditions. The mathematics was correct. The solutions were genuine. But embedded within the analysis, in the careful quantitative estimates that appear later in physics papers and rarely make their way into press releases, were numbers of a particular kind. Numbers that do not announce their significance with dramatic language, but reveal it quietly to anyone who looks closely enough to notice what they are saying. The energy required to generate Lentz's soliton warp geometry, even for a bubble barely large enough to contain a single human being, traveling at just slightly above light speed, was approximately 10 to the 32nd joules. 10 to the 32nd joules. The Sun, our nearest star, radiates energy at a rate of approximately 3.8 times 10 to the 26th joules per second. To accumulate 10 to the 32nd joules, you would need to capture the entire energy output of the Sun, every photon, every neutrino, every quantum of radiation emitted in every direction for approximately 206,000 years. Not use some of its energy. Capture all of it, losing nothing. Converting everything into the specific configuration the warp geometry requires. This is not an energy requirement waiting for better engineering. This is an energy requirement that exceeds the total output of a stellar civilization operating for geological timescales. And this was the optimistic estimate for the smallest possible bubble at the lowest speed Lentz examined. The exotic matter problem had been solved. The energy problem had quietly become several orders of magnitude worse. This is the pattern. Remove one constraint, and a deeper constraint emerges from beneath it, often more severe than the one you removed. The constraints do not operate independently, with each one representing a separate obstacle that might be independently overcome. They interlock. They compensate for each other. When you remove one, the others adjust to fill the gap with something worse. The universe's defense of its speed limit is not a collection of separate locks on a door. It is a structure in which every part supports every other part, and undermining one support causes the load to redistribute onto the remaining supports with increased force. The soliton approach encountered further difficulties beyond the energy problem when examined more carefully. Soliton solutions, by their mathematical nature, are self-sustaining configurations. They maintain their shape through the balance of competing tendencies within their own internal dynamics. This is their appeal. They do not require continuous external energy input to maintain their geometry. But this self-sustaining quality comes with a condition that proves fatal to practical application. Solitons cannot be created from flat spacetime using the same energy that sustains them. The mathematical properties that make them stable once established are precisely the properties that prevent them from forming spontaneously from initial conditions that do not already contain soliton-like structure. Creating a soliton warp bubble from a configuration of flat spacetime and ordinary matter requires a process that is fundamentally different from, and not obviously derivable from, the physics that governs the soliton once it exists. Think of it as the difference between a standing wave in a guitar string and the plucking that creates it. The standing wave is self-sustaining once established. It resonates at a specific frequency, maintaining its shape through the string's elasticity and tension. But you cannot create a standing wave by applying the same gentle, steady force that characterizes the resonance itself. You need an impulsive force, a pluck, something that disrupts the string in a particular way. The physics of creation and the physics of maintenance are different. For soliton warp bubbles, the creation physics involves precisely the kind of exotic spacetime manipulation that the solution was supposed to eliminate. You cannot build Lentz's soliton from flat spacetime using only positive energy. You can potentially maintain it once it exists, but existence must precede maintenance, and achieving existence appears to require the very resources the solution was designed to avoid. The constant velocity solutions face an even more absolute version of this problem. Several theoretical proposals emerging from work by physicists, including Alexei Bobrik and Gianni Martire, published around the same time as Lentz's paper, showed that warp geometries moving at constant velocity through spacetime can sometimes be constructed with positive energy alone. The mathematics is clean, the energy conditions are satisfied, the geometry is consistent, but constant velocity examined carefully means constant velocity for all time, not constant velocity during the journey with acceleration at the start and deceleration at the end. Constant velocity since the beginning of the universe and continuing until its end. These solutions do not describe bubbles that can be created and stopped. They describe eternal features of space-time geometry that either exist as permanent structures woven into the fabric of the cosmos or do not exist at all. You cannot build one. You cannot start one from flat space-time. You cannot stop one at your destination. A constant velocity warp bubble is a geometric artifact that must have always existed and must continue existing forever, carrying whatever happened to be inside it when it formed, or rather, when the universe began containing it on an eternal journey through the cosmos, with no beginning and no end, and no means of boarding or departure. If such structures exist somewhere in the universe formed during the chaotic conditions of the early cosmos, or through processes we have not imagined, they would be extraordinary objects. Regions of spacetime propagating eternally at superluminal velocities, containing whatever matter was present at their formation, unreachable by anything that was not already inside them, unstoppable by any force outside them. Objects of profound theoretical interest. They would not be transportation systems. The word transportation implies origin, destination, departure, arrival. It implies a journey with a beginning and an end. It implies the ability to choose when to leave and where to go and when to stop. A constant velocity warp solution stripped of all these properties is not a faster means of reaching the stars. It is a mathematical structure that the equations permit disconnected from any conceivable practical use. Modified gravity theories offered what seemed like a different path around the exotic matter barrier. General relativity, while extraordinarily well confirmed, is known to be incomplete. It does not incorporate quantum mechanics in any fundamental way. It breaks down at singularities inside black holes and at the initial moment of the Big Bang. Physicists have long sought extensions or modifications of Einstein's theory that might resolve these issues while preserving the theory's successes. Several such modified theories, motivated primarily by attempts to explain dark energy or dark matter without invoking unknown substances, predict slightly different relationships between energy distributions and spacetime curvature. Within certain modified frameworks, the focusing conditions that govern how geodesics respond to energy density take different forms. Some of these different forms appear at first examination to be more permissive regarding the types of geometry they allow with positive energy sources. Papers appeared in the literature showing that specific modified gravity theories permitted warp-like geometries with positive energy alone. These results were presented carefully with appropriate caveats about their theoretical context. The caveats were less prominent in the popular coverage that followed. The problem with this approach emerges when you ask what modifications of general relativity are actually permitted by observation. General relativity has been tested in regimes ranging from the sub-millimeter scales, probed by precision gravity experiments in laboratories, through the solar system dynamics studied by planetary astronomy, to the merger of stellar mass black holes observed by gravitational wave detectors, to the structure of the universe on cosmological scales. At every scale, in every regime, the theory matches observation with precision that has improved steadily as instruments have become more sensitive. Any modification of general relativity must therefore reproduce the theory's predictions in all these tested regimes, while somehow differing in the specific regime relevant to warp drives. The modification must be precisely tuned to affect exotic space-time configurations of the type Alcubierre described, while leaving unaffected the orbital mechanics of Mercury, the deflection of light around the Sun, the gravitational wave, signals from merging black holes, the expansion rate of the universe, and every other context in which the unmodified theory has been verified. This requirement is not merely difficult, it is suspicious in a way that physicists recognize as a warning sign. When a theoretical modification is required to agree with everything we have measured, while disagreeing specifically in unmeasured regimes that would be convenient for a particular purpose, the modification begins to look less like a genuine physical theory and more like a mathematical contrivance, designed to produce a desired result. The modifications that survive experimental constraints tend to produce corrections to general relativity so small that they offer no practical advantage for warp drive construction. The window of viable modified theories that both match all observations and permit easier warp solutions narrows upon careful examination toward a size that approaches zero. Those modifications large enough to make a material difference to warp bubble energy requirements are large enough to produce observable consequences elsewhere that observations have not detected. The focusing theorem presents a constraint that operates at a level below any specific theory, and therefore survives modifications more robustly than proponents of modified gravity approaches might wish. In its most general form, the focusing theorem states that positive energy density causes geodesics to converge to focus toward each other. This is gravitational attraction in its most fundamental geometric expression. It holds not merely in general relativity, but in any theory of gravity that respects certain basic energy conditions considered physically reasonable. A warp bubble requires defocusing of geodesics ahead of the spacecraft. Space must be compressed in the direction of travel, and compressing space means spreading geodesics apart in that direction, which means defocusing them. But positive energy focuses. The focusing theorem says so, and the focusing theorem holds across a wide class of gravitational theories, not just Einstein's specific formulation. To achieve defocusing with positive energy requires finding a regime in which the focusing theorem's assumptions break down. The assumptions involve the energy conditions, mathematical statements about the properties of matter that are considered physically reasonable based on all known forms of matter and energy. All known forms satisfy these conditions. Exotic matter with negative energy density would violate them, which is precisely why exotic matter produces defocusing, and why exotic matter is required for warp bubbles in standard analysis. Modified gravity theories that permit warp solutions with positive energy must in some way circumvent the focusing theorem. They do this by introducing modifications that effectively allow certain positive energy configurations to produce focusing theorem violations in specific regimes. But introducing such modifications while simultaneously satisfying all observational constraints on the focusing properties of gravity in tested regimes requires fine-tuning of extraordinary precision. Fine-tuning in physics is another warning sign. When a theory requires its parameters to be adjusted to precise values to avoid contradiction with observation with no deeper principle explaining why those values should take those specific quantities, physicists become suspicious that theory is not describing fundamental reality but rather has been adjusted to avoid contradictions without genuine explanatory power. A modified gravity theory precisely tuned to permit warp solutions while avoiding observational contradictions has the character of a theory constructed to reach a conclusion rather than a theory discovered by following evidence. This does not prove it is wrong. Fine-tuned theories can occasionally turn out to be correct, with the fine-tuning eventually explained by deeper physics, but it shifts the burden of proof substantially, and the evidence for these theories consists primarily of their mathematical consistency with the desired result, rather than any independent empirical support. Stability analysis completed the picture that energy considerations began, even configurations that appeared to solve the exotic matter problem and satisfy appropriate energy conditions proved upon stability analysis to be dynamically unstable. The warp bubble geometries represent equilibria configurations where forces balance, but they are in most cases unstable equilibria. Small perturbations grow rather than dissipate. The pencil balanced on its point illustrates the concept. Mathematically, this is an equilibrium. The gravitational force pulling the pencil downward passes through the contact point, producing no net torque. The pencil in perfect mathematical conditions could balance forever, but physical reality cannot maintain perfect mathematical conditions. Any infinitesimal deviation from perfect vertical, a vibration from a passing truck, the slight asymmetry of the pencil's mass distribution, a breath of air generates a torque that moves the pencil further from vertical. The deviation grows, the pencil falls, the equilibrium is unstable. Warp bubble geometries are unstable equilibria in multiple simultaneous dimensions. Quantum fluctuations, the same vacuum oscillations that produce the Casimir effect and Hawking radiation, provide continuous perturbations to any macroscopic spacetime configuration. For stable configurations, these perturbations average out over time. For unstable ones, they seed the growth of deviations that destroy the configuration. The time scale for this destruction in most warp bubble configurations examined is extremely short. Quantum fluctuations at the bubble boundary, where spacetime curvature is most extreme, generate instabilities that grow on timescales comparable to the light crossing time of the bubble, the time for light to travel from one side of the bubble to the other. For a bubble large enough to contain a spacecraft, this might be microseconds to milliseconds. The bubble would destroy itself almost instantly after formation, long before any useful journey could be completed. Some researchers have proposed that active stabilization could counteract these instabilities. External systems could monitor the bubble's geometry and continuously adjust the energy configuration to suppress growing perturbations before they reach destructive amplitude. The concept is analogous to active noise cancellation in headphones, continuously measuring unwanted disturbances and generating opposing signals to eliminate them. The problem is that the horizon structure prevents this. Any stabilization system operating from outside the bubble cannot send signals into the superluminal interior. The instabilities grow inside the bubble wall in the region that the horizon structure isolates from external influence. Stabilization from the interior is equally impossible since the spacecraft cannot reach the bubble wall with signals fast enough to matter. The instabilities grow faster than any response can be mounted from any accessible location. The pattern that emerges from examining all these approaches is not the pattern of a field making progress toward a difficult goal. It is the pattern of a field repeatedly discovering that the goal is receding as approaches are refined, that solving each problem reveals the next, with greater severity, that the constraints are not independent obstacles, but a unified structure in which removing one element causes the others to become more binding. Exotic matter requirements emerge from the focusing theorem. Solving the exotic matter problem requires either violating the focusing theorem or finding modified gravity theories that circumvent it, but those modifications are constrained by observation to be negligibly small. Even if exotic matter were available, the energy quantities required for functional warp geometries vastly exceed stellar outputs. Even if energy were available, the horizon structure prevents navigation and control. Even if navigation was solved through pre-programming, instabilities would destroy the bubble before journey completion. Even if stabilization were achieved, causality preservation mechanisms would eliminate any configuration approaching a causality violation. Each constraint supports the others. Remove any one, and the weight shifts to the remaining ones with greater force. The defense is not a wall. It is a lattice, and every node of the lattice connects to every other node, so that weakening any node simply redistributes the structural load. What does this tell us about the relationship between the universe we can describe mathematically and the universe that physically exists? That question is not merely philosophical. It touches something fundamental about the nature of physical theory and what it means for an equation to describe reality. The gap between mathematical permission and physical possibility, which warp drive research has mapped with such clarity and at such cost in theoretical effort, reveals a feature of our universe that deserves to be taken seriously as a discovery in its own right. We have been treating the cosmic speed limit as a barrier to be overcome. Perhaps we should be asking what it tells us about the structure of the universe that it is enforced this way through redundant, interlocking, mutually reinforcing constraints, each emerging from deep principles at the foundations of physics, each connected to the others through relationships that only become visible when you try to break them. Perhaps the speed limit is not a barrier at all. Perhaps it is a load-bearing feature of the architecture of reality. Perhaps the question is not how to circumvent it, but what we learn about the universe by discovering that it cannot be circumvented, and whether that knowledge honestly received changes how we understand our place in the cosmos that continues. That is the question the final chapter of this story was always building toward. There is a particular kind of knowledge that only becomes available through failure. Not the failure of insufficient effort or inadequate resources, not the failure of an experiment that could be redesigned, or an instrument that could be made more sensitive, or a calculation that could be corrected. The failure of an idea that was pursued with full rigor, with complete mathematical honesty, with the best theoretical tools available, and that returned not a path forward, but a map of why no path exists. This kind of failure is rarer than it sounds. Most failures in science are contingent. They depend on circumstances that might change, on knowledge that might improve, on technology that might advance. The failure of the warp drive program accumulated across 3 decades of increasingly sophisticated analysis has a different character. It is the failure of a mathematically precise concept, encountering physical constraints that operate at the deepest levels of natural law, constraints that become more severe the more precisely the concept is examined, constraints that connect to each other through relationships that would need to be simultaneously dismantled for any version of the concept to work. This kind of failure teaches things that success cannot. Consider what we have learned by attempting to circumvent the cosmic speed limit through the warp drive approach. We have learned that general relativity's field equations are more permissive than the physical universe, that mathematical solutions to the governing equations describe configurations that physical reality excludes through mechanisms operating at levels the classical equations do not capture. We have learned that exotic space-time configurations trigger quantum instabilities that classical analysis would never reveal. We have learned that the focusing theorem, the quantum inequalities, the causality preservation mechanism, and the horizon structure of superluminal geometries all connect to each other through threads that only become visible when you put on them simultaneously. We have learned, in other words, something about the architecture of physical law that we could not have discovered any other way. The pattern of interlocking constraints that protects the cosmic speed limit resembles in structure, if not in detail, other deep features of physical law that we have come to recognize as genuinely fundamental rather than contingent. The conservation of energy, the second law of thermodynamics, the uncertainty principle. These are not arbitrary rules imposed on a universe that might just as well have operated differently. They are structural features of reality, whose interconnections run so deep that modifying any one of them would require modifying everything connected to it, which is to say, everything. The speed of light is woven into physics in precisely this way. It appears in Maxwell's equations governing electromagnetism. It appears in the relationship between electric and magnetic fields. It appears in the structure of spacetime through Einstein's special relativity. It appears in the conversion between mass and energy through the equation that even people who know no physics can recite. It appears in the quantum mechanical description of particle interactions in the coupling constants that determine the strengths of the fundamental forces in the fine structure constant that governs the interaction between light and matter, and therefore determines the size of atoms, the energies of chemical bonds, and the wavelengths of light that eyes like yours evolved to detect. Change the speed of light, and you do not simply change a speed limit. You change electromagnetism, which changes chemistry. You change chemistry, which changes biochemistry. You change biochemistry, which changes biology. You change biology, which changes the conditions that permitted the evolution of creatures capable of measuring the speed of light and wondering whether it could be exceeded. The constraint that frustrates our cosmic ambitions is inseparable from the physical conditions that produce the ambitions in the first place. This is not a coincidence that demands explanation. It is the signature of a universe whose properties form a self-consistent whole rather than a collection of independent parameters that might be adjusted separately. The speed of light is not a dial that could be turned up without consequence. It is a structural constant whose value permeates the equations governing every physical process, from the formation of hydrogen atoms in the early universe to the firing of neurons in the brain reading these words. A universe with a higher speed of light would be a different universe in every physical respect, not our universe with faster light. A different universe with different atomic structure, different chemistry, different stars burning at different rates, different timescales for planetary evolution, different conditions for whatever forms of complexity its physics permitted. Whether that universe could contain beings who looked up at the night sky and wondered about the distances between stars, we cannot say. But it would not contain us. We are products of this universe's specific physical constants, and the speed of light is among the most fundamental of them. The prison and the home are the same structure. This phrase carries more weight than it initially seems to carry. The cosmic speed limit confines us to our stellar neighborhood on any timescale meaningful to human civilization. No warp drive will carry our descendants to distant galaxies. No shortcut through space-time geometry will compress the 4 light-years to Alpha Centauri into a journey of days. The stars we see on clear nights are points of light that took years, decades, centuries, millennia to reach our eyes. And reaching back to them with any physical presence would require comparable investments of time, even at the very best velocities our physics permits. This is confinement. Genuine, absolute physics-enforced confinement, not confinement that technology will eventually overcome, confinement that reflects the nature of the universe we inhabit. But examine what this same universe has provided within the confines it imposes. The observable universe spans approximately 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies. Each galaxy contains on average hundreds of billions of stars. The Milky Way alone harbors between 100 billion and 400 billion stellar systems, and recent surveys suggest that most stars host planetary companions. The fraction of those planets orbiting within the habitable zones of their stars, where liquid water might persist at the surface, runs into the billions for our galaxy alone. Within this confinement, we possess more worlds than our species could visit in any conceivable span of existence, more stars than could be catalogued in 10,000 human lifetimes of uninterrupted counting, more potential homes for complexity than any civilization could meaningfully explore regardless of its longevity. The confinement is not poverty. It is an abundance so extreme that the limitation feels almost academic. We cannot reach the Andromeda Galaxy in any meaningful time, but we have not yet visited everybody in our own solar system. We have not landed human beings on Mars. We have not sent probes through the atmospheres of the gas giants, or landed on the moons of Saturn. We have not fully characterized the Kuiper Belt or the Oort cloud. The nearest star system, the one that serves as the reference point for all discussions of interstellar distance, remains entirely unexplored. Everything we might realistically do in space for the next 1,000 years lies within a volume of the cosmos so small, relative to what exists, that labeling it confinement requires a generosity of definition. The speed limit confines us. The universe does not. The history of physics contains a distinguished tradition of productive impossibilities, constraints that at first appeared as failures of human ambition and subsequently revealed themselves as windows into fundamental truth. In the 19th century, physicists pursuing the dream of perpetual motion machines that would run forever without energy input encountered what appeared to be a frustrating series of engineering failures. No matter how clever the design, some mechanism of friction or heat loss or resistance always drained the machine's energy until it stopped. The impossibility of perpetual motion looked like a technological limitation, a reflection of insufficient engineering sophistication. It was not. It was the thermodynamic laws announcing themselves through the accumulated failure of many experiments. The impossibility of perpetual motion encoded the conservation of energy and the inexorable increase of entropy principles that govern everything from the efficiency of engines to the ultimate fate of the universe. The failure of every perpetual motion machine was the universe teaching thermodynamics through the only language that would compel attention, the repeated collapse of clever schemes. In the early 20th century, physicists attempting to describe atomic spectra encountered another frustrating impossibility. Classical physics predicted that electrons orbiting atomic nuclei should continuously radiate energy and spiral into the nucleus within a fraction of a second. No stable atom should exist. Yet atoms were stable. The impossibility of stable atoms within classical physics was the quantum revolution announcing itself. The failure of classical mechanics to account for atomic stability drove the development of quantum mechanics, which revealed that reality at the atomic scale operates according to principles utterly unlike anything classical physics imagined. Each impossibility opened onto a deeper and more complete understanding of physical law. The failure was not the end of inquiry. It was the beginning of deeper inquiry, the forced abandonment of insufficient frameworks in favor of more accurate ones. The impossibility of warp drives belongs to this tradition. The decades of theoretical effort, the accumulating constraints, the pattern of problems compounding rather than resolving these are not signs of a program that failed to find what it sought. They are signs of a program that found something more important, a precise map of why the sought thing does not exist, drawn with the rigor that only mathematics can provide, revealing connections between physical principles that had not previously been seen to connect. This map is not the consolation prize. It is the discovery. Consider what warp drive research has revealed about the relationship between classical and quantum physics in curved spacetime. Before the detailed analysis of warp, bubble stability, and quantum back reaction, the interaction between quantum field theory and exotic spacetime geometries was poorly understood. The calculations forced by the need to evaluate whether warp bubbles were stable against quantum fluctuations drove developments in semi-classical gravity, the study of how quantum fields behave in classical curved spacetime backgrounds that have applications far beyond warp drive physics. The quantum inequalities that Ford and Roman derived while studying what negative energy configurations quantum mechanics permits represent genuine theoretical advances. They constrain not just warp drives, but any process involving negative energy density, including the Casimir effect, Hawking radiation from black holes, and the behavior of quantum fields during cosmic inflation. Understanding these constraints more deeply illuminates the quantum structure of spacetime in ways that matter for physics entirely apart from the question of faster-than-light travel. The analysis of horizon structures in superluminal geometries has connections to black hole physics. And the information paradox, the still unresolved question of what happens to information that falls into a black hole. The mathematical tools developed to analyze warp bubble interiors connect to tools used to study black hole interiors, and insights flow in both directions. The impossibility of warp drives has been theoretically productive in ways that would not have occurred without the attempt. This is what impossible things teach us. They teach us where the walls are, and in teaching us where the walls are, they teach us what the walls are made of, and in teaching us what the walls are made of, they illuminate the structure of the building that the walls support. We are creatures who look at walls and wonder what lies beyond them. This is one of our most characteristic and admirable traits. We should not abandon it. But wisdom also requires knowing which walls are doors waiting to be opened, and which walls are foundations without which the building falls. The cosmic speed limit appears to be a foundation. 3 decades of rigorous theoretical assault have not found a door within it. They have found only deeper understanding of why it stands. There is a loneliness in this conclusion that deserves acknowledgement before we move past it. The Fermi paradox, the observation that a universe containing billions of potentially habitable worlds should by naive probability also contain many civilizations more advanced than ours, none of which we have detected, has occupied physicists, astronomers, and philosophers for decades. The apparent silence of the cosmos, the absence of signals from technological civilizations that should by some estimates be abundant, has generated dozens of proposed explanations ranging from the optimistic to the deeply unsettling. The cosmic speed limit offers one explanation that requires no catastrophe, no great filter, no tendency for civilizations to destroy themselves before achieving interstellar reach. It offers instead a simple geometric fact. Civilizations separated by light years cannot meaningfully communicate on human timescales, and at interstellar distances, even the speed of light produces delays of years, decades, centuries between transmission and reply. The nearest star system from which a civilization could have detected evidence of Earth's technological activity, radio emissions, atmospheric signatures of industrial chemistry, is close enough that signals from them would take 4 years to arrive, and our replies would take 4 years to return. An 8-year round trip for a single exchange. Andromeda, the nearest major galaxy, lies 2.5 million light-years distant. A signal sent today would arrive in 2.5 million years to whatever civilization might exist there in that unimaginable future. Their reply would reach us 5 million years from now. Even if the universe teems with intelligence, even if every suitable star hosts civilizations of arbitrary sophistication and goodwill, the speed limit transforms the cosmos into a collection of isolated conversations conducted across geological timescales. Not silence because no one is speaking, silence because the words take longer to arrive than civilizations endure. Each civilization exists within its light cone, the region of space-time that can be causally connected to it given the universal speed limit. Within that light cone, communication is possible though slow across interstellar distances. Outside it, contact is geometrically forbidden regardless of technology or intention or desire. The light cone expands at the speed of light in every direction, growing larger with each passing year, but slowly by cosmic standards. In the entire history of human technological civilization, 10,000 years, from the first cities, our light cone has expanded only 10,000 light-years in any direction, a tiny fraction of one galaxy among trillions. We are not isolated because we are alone. We may be isolated because the universe is structured so that beings like us, however abundant, cannot readily find each other across the distances that separate them. The silence may not be emptiness. It may be the sound of a cosmos full of voices speaking in languages that take longer to arrive than the civilizations that speak them typically last. This is a particular kind of solitude, not the solitude of the only candle in a dark room, Potentially the solitude of a candle that cannot see other candles burning in rooms too far away for light to have traveled between them in the time both candles have been lit. The other flames may burn. The darkness between them is not their absence. It is the geometry of the space that separates them, enforced by the same principles that prevent the shortcuts we have spent this journey trying to find. The solitude is not a punishment. It is a consequence of existing in a universe with a specific geometric structure, a structure that produced, among other things, the conditions for stars to form, planets to coalesce, chemistry to occur, life to evolve, and minds to arise that can contemplate the geometry confining them. The same universe that isolates us created us. The same principles that prevent interstellar communication at human timescales also govern the nuclear reactions that power the sun, the chemical bonds that hold our molecules together, the electromagnetic interactions that allow our eyes to receive light from distant stars, and our brains to wonder what burns within them. The light that reaches us from other stars is in a sense the only form of contact the universe permits at these distances. Ancient light departed from its source years or centuries or millennia ago, carrying information about conditions that no longer exist at a place we cannot visit. We receive it, we analyze it, we learn from it. We cannot reply at any speed that the source would recognize as timely, but consider what we have done with that light. From the spectra of distant stars, we have determined their chemical compositions, their temperatures, their velocities, their ages, their masses. From the wobble of starlight, we have inferred the presence of planets too small and distant to see directly. From the dimming of starlight in transit, we have characterized atmospheres on worlds orbiting other suns. From the ancient light of galaxies, billions of light-years distant, we have reconstructed the history of the universe from its first moments to the present day. From a beam of light that traveled 2.5 million light-years from the Andromeda galaxy before entering a human eye, we have determined that Andromeda contains approximately 1 trillion stars and will collide with the Milky Way in approximately 4.5 billion years. We have read the universe from the light it sends us sitting still on one planet, looking outward with instruments that become more sensitive with each generation of their construction. The confinement has not prevented understanding. In some ways, it has focused understanding, forced us to learn everything we know about the cosmos, from the information that the cosmos volunteers through the single channel the speed limit permits. That channel is extraordinary, and what it has revealed is a universe more strange, more vast, more ancient, and more intricate than any previous generation of humans could have imagined. Not a diminished universe narrowed by the speed limit. A universe whose full extent we are only beginning to appreciate, constrained not by our ability to reach its contents, but by the time it takes light to carry news of those contents to our instruments. The stars are telling us about themselves. They have been telling us for as long as we have had eyes to receive the message. We are only now developing the sophistication to understand what they say. 1424, Claude responded. We began with a number. 4.2 light-years, the distance to the nearest star beyond our sun, a number so familiar to anyone who has spent time reading about space that it has almost lost it. End quote. We say it casually the way we say other large numbers that we understand intellectually but have never truly felt. 4.2 light-years, the nearest one. The closest campfire in a darkness that extends in every direction without meaningful boundary. We have traveled a long way since that opening number. We have gone from the patent office in Bern, where a 26-year-old clerk dismantled Newtonian physics with 4 papers through the geometric revelation that mass curves spacetime, and spacetime tells mass how to move through the elegant and devastating mathematics of a warp bubble that Einstein's own equations accept without objection through the exotic matter that cannot exist in sufficient quantities, through the horizon that prevents steering through the causality loops that the universe appears determined to prevent at any cost, through the soliton solutions that require the energy output of stellar civilizations, through the constant velocity bubbles that cannot be created or stopped, through the modified gravity theories that cannot survive observational constraints, through the stability problems that quantum fluctuations solve in microseconds by destroying what took theorists years to construct. We have mapped with considerable precision every approach to the wall. We have found at every approach the same answer. The math allows it. The universe resists it. Not with one mechanism, with many. Not through a single prohibition, but through an interlocking lattice of constraints, each emerging from deep physical principles, each connected to the others, through relationships that only became visible when we pulled on them. Remove exotic matter requirements, and energy demands grow by orders of magnitude. Solve energy demands and horizon structures, prevent control. Circumvent horizon structures and causality mechanisms, obliterate the configuration before completion. Work around causality, protection, and quantum instabilities arise at the bubble boundary, destroying the geometry on timescales of microseconds. Each solution opens onto a deeper problem. Each apparent loophole seals itself as you approach. This is not the picture of a technology that awaits better engineering. It is the picture of a prohibition woven into the fabric of reality, at a level deeper than any equation we have written. And yet, the journey has not brought us to despair. It has brought us somewhere more interesting than despair, and more honest than the false comfort of thinking the stars are simply waiting for us to become clever enough to reach them quickly. It has brought us to a place where the question changes, where we stop asking how to circumvent the speed limit and begin asking what it means that the speed limit exists in the form that it does, enforced in the way that it is connected to everything that it connects to. What it means is this: the cosmic speed limit is not a cage, it is a consequence of the same physical structure that produced the stars. The limit keeps distant the planets that orbit those stars, the chemistry that makes those planets potentially habitable, the biology that might arise in that chemistry, and the minds that might look up from those planets and wonder about the distances between them. The speed of light is not imposed on a universe that would otherwise permit faster travel. It is woven into the equations that govern electromagnetism, that determine the size of atoms, that set the rates of chemical reactions, that govern the nuclear burning of stars, that determine whether planets form at the right distances for liquid water, that govern the replication fidelity of molecules carrying hereditary information. Change the speed of light, and you do not simply change a speed limit. You change everything. You change the fine structure constant that governs how atoms absorb and emit light. You change the stability of matter. You change the timescales on which stars burn and planets cool and chemistry operates. You change in ways impossible to predict with confidence whether anything like us would exist to be frustrated by the new speed limit, or grateful for its absence. We are not trapped by the speed limit. We are in some deep sense a product of it. The universe that produced us is the universe with this speed limit, not a more convenient universe, not a universe better suited to our travel ambitions. This universe, with these constants, with these constraints, which turned hydrogen and helium into stars, stars into heavier elements into planets, planets into the conditions for chemistry, chemistry into the conditions for life, life into the conditions for minds, and minds into the capacity to measure the speed of light and wonder whether it could be exceeded. This capacity to measure, to wonder, to construct mathematical frameworks that describe configurations the universe forbids, and then to understand precisely why they are forbidden, is itself extraordinary. Consider what it requires. It requires nervous systems sensitive enough to detect the dimming of a distant star as a planet passes before it. It requires mathematical languages sophisticated enough to write down the geometry of a warp bubble and solve for its energy requirements. It requires the ability to hold in mind simultaneously the observable universe containing 2 trillion galaxies and the quantum vacuum fluctuations operating at scales trillions of times smaller than an atom. It requires the patience to pursue theoretical programs across decades when the results are consistently disappointing. It requires the honesty to report those disappointing results accurately, rather than adjusting them toward more comfortable conclusions. It requires, in short, everything that makes us remarkable despite our smallness. We are not the largest things in the universe. We are not the most energetic. We are not the most massive, or the most ancient, or the most numerous. A single hurricane contains more energy than our entire civilization produces in a year. A single solar flare releases more energy in minutes than humanity has used in all of recorded history. The galaxy contains 400 billion stars, each one burning for billions of years, each releasing energy on scales that make our industrial civilization appear negligible to the point of invisibility. And yet, we have measured the expansion rate of the universe. We have detected gravitational waves from black hole mergers a billion light-years away. We have determined the chemical composition of stars from their spectra. We have calculated what happened in the first seconds after the Big Bang. We have worked out the mathematics of space-time geometries that would permit warp travel, and then worked out the mathematics of why they cannot be constructed. We have held the entire observable universe in our minds, turned it over, examined it from multiple angles, and begun to understand its structure. The universe is approximately 14 billion years old. It contains structures ranging from subatomic particles to galaxy superclusters. In all that time, across all that scale, on one small planet, orbiting one unremarkable star in one of 2 trillion galaxies, something arose that could do what we have just done together in this conversation. Something arose that could ask why the stars are distant, and answer the question. Not with myth or speculation, but with mathematics and measurement, with theories tested against reality and revised when reality disagreed. This is not a small thing. This may be the most extraordinary thing the universe has yet produced, measured not by size or energy, but by what it can do. The speed limit will hold. It has held since the universe was young enough that the cosmic microwave background radiation was still visible light, rather than microwave frequencies. It held through the formation of the first stars and the death of the first supernovae, and the coalescence of the first planetary systems, and the emergence of the first living things, and the long, slow climb of complexity that led after billions of years to a species that could calculate why it floats. Alpha Centauri remains 4.2 light-years away. The journey at any velocity our physics permits would take years, decades, generations, depending on the technology available and the patience invested. Our descendants may someday make that journey carried across the void by patience and determination and engineering that would seem miraculous to us, spending years or decades in transit, arriving at another star system as explorers who left, knowing they would not return in their lifetimes, or their children's lifetimes, or their children's children's lifetimes. That journey will be extraordinary, not because it is fast, because it is real, because it will be made by creatures who understood the distances before they crossed them, who knew what they were doing and why it was worth doing and what it cost and what it meant. Creatures who looked at the void and decided over generations of effort and sacrifice that the void was worth crossing, even at the speed the void permits. No warp drive will carry them. The universe has been clear on this point through every investigation we have undertaken. The shortcuts do not exist in physical reality, only in mathematics. The mathematics is beautiful, and what it teaches us by failing to describe reality is valuable, and the failure is instructive in ways that success would not have been. But the stars are reached, if they are reached at all, through patience and time and the willingness to accept what the universe actually offers rather than what we would prefer it to offer. What it offers, honestly examined, is not poverty. It offers a night sky visible from the surface of this planet, on clear evenings containing more stars than can be counted in a human lifetime. Each one a sun, many of them accompanied by worlds, all of them burning with nuclear fire, all of them sending light across the void to fall on human faces. It offers a cosmos 14 billion years old that we have learned in a few thousand years of systematic inquiry to read with considerable accuracy. It offers the knowledge of our own smallness, alongside the knowledge of our own extraordinary capacity for understanding. It offers the challenge of a universe that does not bend to our wishes, but rewards our curiosity with genuine discovery. It offers the stars themselves not as destinations we can quickly visit, but as presences we can genuinely know. We know what they are made of. We know how they burn. We know how they are born from collapsing clouds of gas, and how they die. Some gently fading, some exploding outward with enough energy to outshine the galaxy for weeks. We know their ages, their masses, their compositions, their temperatures, their magnetic fields, their internal structures. We know more about a star 4 light-years away than our ancestors knew about rivers and mountains within walking distance of their homes. This is what the speed limit gives us alongside what it takes. It takes the quick journey. It gives us the time and the reason to truly look. The light arriving from Alpha Centauri left its source 4.2 years ago. The light arriving from the Andromeda Galaxy departed 2.5 million years in the past, when our ancestors were still learning to shape stone into tools. The light arriving from the most distant objects in the observable universe has been traveling for over 13 billion years, departing when the universe was less than 1 billion years old, and the first stars were only recently formed. Every observation we make of the cosmos is an act of archaeology. We do not see the universe as it is. We see it as it was at times ranging from nanoseconds ago for objects within our solar system to billions of years ago for objects at the edge of the observable universe. The speed limit that prevents us from reaching distant objects also means that the information those objects send us carries the history of the cosmos written in light. The universe is its own archive, and the speed of light is the rate at which that archive delivers its contents to any point within it. We are surrounded on every clear night by history, by ancient light that has crossed distances our minds cannot intuitively grasp, carrying information about conditions that existed before our planet, formed before our star, ignited before the molecular cloud that would eventually become our solar system had begun to collapse. That light falls on us. We can receive it. We can decode it. We can understand from that light alone sitting on the surface of one planet the large-scale structure of a universe containing 2 trillion galaxies. The warp drive does not exist. The shortcuts are closed. The wall stands not as a single barrier, but as the surface of the universe's own self-consistent structure, enforced by principles so fundamental that circumventing them would require a different universe entirely, one that might not contain anything capable of wanting to circumvent to them. What we have instead is this: a planet, a sky full of ancient light, the capacity to understand what that light is telling us, and enough universe within our reach, even at the speeds physics permits, to occupy our curiosity and our courage for as long as our species endures. The stars are not waiting for us to find a shortcut to them. They are waiting at the distances they occupy, burning in the darkness, sending light in all directions, some small fraction of it falling on this small world, entering eyes that evolved to detect it, reaching minds that learn to interpret it, arriving as it always has and always will at the only speed the universe allows, 300,000 kilometers per second, slower than we would wish, faster than anything else the cosmos contains, enough to carry the light of a candle burning on the surface of a pale blue dot outward through the dark in every direction for as long as the candle burns. The candle is burning now. The light is already on its way.